Hi, I'm Jason with SSAI. Today we are exploring NASA's WHyMSIE mission. Stay tuned as Stephen, Peter, and Jen help break this mission down. Speaking of scientists, we have 3 rock star guests who are joining me today. We have members of the WHyMSIE team at NASA Goddard Space Flight Center, Stephen Nicholls, who is a returning guest, Peter Pantina, and Jen Moore. Stephen, Jen, and Peter, I just wanted to say thank you all so much for taking time out of your very busy schedules to talk with me today. How are you all doing today?
Doing just great. Yeah. Enjoying the snow, fun little weather going on outside, and glad to be here.
Yes, indeed. If you're along the East Coast, we definitely have gotten a winter storm. So please definitely go outside and sled if you wanted to, but also be careful if you are traveling as well. And we also wanted to wish everybody a Happy New Year as well. So we are very excited here at SSAI to keep rolling with our projects in 2025. So we are very excited to have you listening in. And I think as we can all agree, Stephen, Jen, and Peter, it is a great day at SSAI. Am I correct?
Indeed. Yep.
Awesome. Well, with that, Stephen, Jen, and Peter, what I wanted to do is I wanted to ask each of you some questions in relation to your work that you have done at SSAI, and especially your work with the WHyMSIE mission that has occurred. So my very first question that I wanted to ask you all was to please tell the audience about yourself and describe your projects you have worked on with the WHyMSIE mission at SSAI. Stephen, would you mind kicking us off?
Sure, I'd be glad to. As far as myself, I'm a senior research scientist at SSAI, coming up on my 5th year working for SSAI, and been working at Goddard Space Flight Center for nearly 12 years as of this coming March. My main role with NASA is focusing more on model and instrument analysis. And of course, I had an involvement with the WHyMSIE field campaign, where my role within the WHyMSIE field campaign focused on 3 main objectives. One being the one that I was involved with the mission scientist role, where within this role, I was helping to plan and operate ground-based observation planning and support for the WHyMSIE field campaign. Coordinating the overall mission schedules, we call these plans of the day. So as Peter and Jen would probably know, I sent these out daily, at least when I was on site, basically saying, well, what was the overall plan? What science objectives did we have? What were you looking for? And then in addition to, because I also worked on the weather forecasting work for WHyMSIE, was to also provide weather context for mission flight planning with the head mission scientists in terms of planning flights, where they're going to fly, and how it meets their objectives for the day. As like a weather forecaster, my main role is mainly coordinating and working with other mission weather forecasters to build daily weather briefs, which were crucial for flight planning, determining what days we could fly. And also within the same context to provide airfield condition forecasts, given the high sensitivity, particularly of the ER-2 aircraft, to wind conditions at the airfield. And then finally, one of my roles, which is still ongoing, is analyzing the Cosmere H data with respect to what we call obs minus calc. Because since Cosmere H is actually a brand new instrument, we need a way to help validate it against existing data to see, well, does our data make sense? Is it practical? Or are we seeing reasonable answers? And so part of my role with this is basically taking the Cosmere H data and then differencing this from simulated data of Cosmere H to determine how, you might say, sensical the data is.
Wow, that's awesome, Stephen. And I really appreciate you highlighting even further in terms of your role and responsibility. So there definitely was some administrative work that you did as well, but that's great to hear about all the science that was involved that you did throughout this mission. So thank you very much. And again, welcome back. I know we featured you on a previous podcast episode, so it's great to see you again.
It's great to be back. Glad to say the weather station's still working fine. So
Indeed, absolutely. Peter, I'm going to transition over to you next. Would you mind telling the audience about yourself and describing your projects you have worked on with the WHyMSIE mission at SSAI?
Sure. So I'm a lead systems engineer at SSAI. And I guess like Stephen, I've also been here for 12 or 13 years now. So I work on site at NASA Goddard. So for the WHyMSIE campaign last fall, I helped to integrate, test, calibrate, and operate 2 instruments on the ER2. One of them was a radar called MBARS. It's a V-band, downward pointing, pressure sensing active radar. The other instrument was an IR imager, kind of like basically a camera, whose main purpose was to detect and characterize any smoke plumes that we flew over. So during this mission, in addition to installing and operating these instruments, I also helped to downlink data and prepare kind of the network configurations to make that happen. So downlink data from the airplane to the ground so that we can look at images in real time. And that helped the PIs and people like Stephen to kind of make changes to the flight path on the fly if they needed to. If they see a cloud coming up or smoke plume coming up, they can talk to the pilots and change the direction of the plane to overfly that a little bit more. So that's my basic role. And now that we're back home at Goddard, I do a lot of data processing, processing navigation data, producing visualizations, things like that. So it's a mix of engineering and data processing is what I do.
That's awesome, Peter. And I really appreciate you highlighting about your experiences that you currently do, especially as a lead systems engineer. So definitely there's a lot of engineering that goes into work like the WHyMSIE mission. So I really appreciate you highlighting more about your role there. Jen, I wanted to transition on to you next. Can you tell the audience about yourself and describe your projects you have worked on with the WHyMSIE mission at SSAI?
Yeah, so I'm a programmer / analyst for SSAI. I guess I'm one of the newer employees. I started back in January of last year, and I work on site at NASA Goddard with CPL, so the Cloud Physics Lidar. So the LiDAR has 3 wavelengths, 355, 532, and 1064 nanometers. So it looks in infrared, UV, and the green spectrum. And I guess because I'm relatively new, I was just out of school last year. So I got my bachelor's in meteorology from Millersville University, and then my master's in atmospheric science from the University of North Dakota. For the WHyMSIE field campaign, again, I worked on CPL. So a big part of my role is kind of similar to Peter's, where I work on in the field integrating CPL onto ER2. I support CPL during the mission by running real-time data scripts, which again, similar to Peter's instruments, they're used in real time to kind of help people like Stephen figure out where we need to go real time. And then after the mission, I do a lot of quick processing scripts. So now that we're back home, I can actually go in and start kind of finagling and enhancing CPL's data products.
That's wonderful, Jen. And by the way, I just wanted to say congratulations on your bachelor's and your master's degree as well. So that's an incredible accomplishment. Jen, I really appreciate you highlighting about your educational background and what you currently have done with the WHyMSIE mission. And Peter and Stephen, same to you as well. Thank you all so much for highlighting your roles with the WHyMSIE mission. I now wanted to transition onto a question that, Stephen, I was going to ask you next. As one of the lead forecasters, like you mentioned, and one of the mission scientists for the WHyMSIE mission, you have a critical role in validating the Cosmere H sensor. Could you share how this groundbreaking sensor, with its 6,148 channels, is advancing our understanding of atmospheric science, and what excites you the most about its future applications?
Well, I'm very glad to expand upon this, but also just want to give a quick shout out to the fact that WHyMSIE, although its main focus was on the validation of the Cosmere H sensor, it was really a team effort across all the different sensors, including CPL, the radars, the ground sensors. It really was a team effort to make everything work and function as well as it has. As far as Cosmere H itself, is that actually, if you look behind me now, the data behind me is actually data from Cosmere H from a November 4th flight of 2024. But over here you have San Francisco Bay, and then you go all the way over to here, you have Lake Tahoe over my left. So this gives you an idea geographically what COSMER H data provides, which is that COSMER H can both look at areas like near the surface. So as you see here, you clearly see San Francisco Bay on my right, and you see Lake Tahoe on my left. But if you look at like different channels, you look like up to here, you see there's hardly any information at all. You don't see information about the surface. So what COSMER H really provides you is it provides data between 50 gigahertz and 191 gigahertz. Now, what this does is that this allows you to see data from a multitude of different perspectives. So in particular, the COSMER H, which is the conical scanning microwave imaging radiometer hyperspectral, just to throw that in, is actually based upon a sensor which actually preceded it called COSMER. So COSMER, no H. The difference is that COSMER H actually takes the COSMER instrument, which only had 9 channels originally. So as you mentioned earlier, it's 6,000 channels now. It originally was 9. So what you did is that you take the receivers, which are at 50 and 183 gigahertz, which provides you the near surface information and the water vapor information, and you replace these with hyperspectral receivers. Now, for anybody that's not familiar with this, is that so you might ask, I keep mentioning this magical word hyperspectral. So what this means is that between 50 and 58 gigahertz and 175 to 191 gigahertz is COSMER H provides a spectral resolution of 4 megahertz. So this is how you equate to getting up to 6,000 channels. You take that 50 to 58 gigahertz hyperspectral range plus the 175 to 195 gigahertz range. You add in 2 polarized frequencies at the 89 and 165 frequency range, and then you get this grand total of 6,148 channels that you mentioned earlier. But as far as the actual deliverable here is that the big thing is going from 9 to 6,000 channels. It's huge, especially because the previous instrument in COSMER tended to average across a relatively wide swath of frequencies, where it used to be said they do 183 gigahertz plus or minus 7 gigahertz. So you average across that entire range of data. And so you actually get good quality data with that, but you lose potential information and structure in the atmosphere because you're averaging across all those frequencies. So what COSMER H offers is that it provides the potential of having a much greater vertical resolution of data, because you have all these different frequencies, and each of these frequencies emits at different levels in the atmosphere, which we can convert and work to get information about temperature and relative humidity throughout the entire profile. And in particular, as compared to existing infrared sensors such as AIRS, is the microwave instruments are not as sensitive or not as attenuated as compared to the infrared instruments. So this gives you a greater ability to see into cloud systems without the signal getting attenuated, at least to the point where you don't have heavy precipitation, because at that point, you don't have anything at that point. But the advantage of COSMER H, though, is that each of these frequencies provides different information, where your lower frequencies, your 50 to 58, is your lower atmospheric profile. So this gives you your planetary boundary layer temperature, relative humidity. You have 89 gigahertz, that they have the non-hyperspectral 89 gigahertz, which is clouds and precipitation. You have the 165, which provides you information about cloud particles, light precipitation. And then finally, between 175 and 191, you get information about the vertical structure of water vapor. And so what COSMER H really provides you is you get information about, again, your temperature, your moisture structures throughout the atmosphere. And in particular, as compared to the existing sensor ATMS, which is the current microwave standard in space, is COSMER H provides much more information, particularly about the mid-troposphere, which is currently a region which is not well resolved by existing microwave instruments in space. So, but notably, though, is that COSMER H, though, does have one minor weakness, which is actually addressed by the WHyMSIE campaign, which is that the reason why we needed all these additional information from CPL, from CRS, from other instruments such as AMPER, is because we need to provide context for all these measurements. Because again, COSMER H is a fairly new instrument. Now, we know it works, but we have to make sure it's sensible and it provides information. So in addition, is that to provide information about, particularly about the surface, is COSMER H did require the being co-located, particularly with an instrument called AMPER, or the Advanced Microwave Precipitation Radiometer, which provided even lower frequencies at 10, 19, and 37 gigahertz, which helped us provide much more information about the surface information. which is currently an area under development for Cosmere H, being that the return from Cosmere H can vary considerably depending upon what type of surface you fly over. Such as we had an example, I think it was the October 23rd flight. We flew over the Midwest twice over the site called the Southern Great Plains, of where we had a case where the ground was dry, the ground was wet, but the retrievals from Cosmere H were actually vastly different between A and B because you had wet soil in one case and dry soil in the other case. So to answer your question and just to finish up, so what excites me the most about Cosmere H data is that the greatest thing about this is that, well, one, we're not going to eventually use all 6,000 channels. That's too much to analyze, too much data to process. So it's all about finding the most efficient way to use all these different channels to provide the most amount of information about these profiles. And in particular, is that given that current instruments have maybe tens of levels in them, we're going to potentially having hundreds of levels of information, providing information about temperature and relative humidity, which will eventually be flown in space with an upcoming space instrument called Aurora, which will be the first hyperspectral microwave instrument in space, which is planned for a little later on, but is under development. But in this case, the promise of Cosmere H is getting towards providing a proving point for hyperspectral instruments, providing unprecedented details of temperature and vertical structure in the atmosphere from space, and be able to provide this for weather model analysis and providing this information for forecasting, planning, and just overall science.
Wow, Stephen, that is absolutely incredible. And that is very fascinating. You know, based on everything that you have just explained, I'm just super excited to see what continued data we are going to get in relation to the overall process, you know, with weather and our climate from Earth in relation to all these different instruments. So, and the fact that you were able to take it, you know, from 9 channels, like you said, all the way up to, you know, 6,000, that's pretty significant and that's pretty incredible. And, you know, definitely looking into the efficiency aspect in terms of how to use all those instruments is very key, and it's very important in order to get some important data. So I really appreciate you going into deeper analysis in relation to the Cosmere H sensor instrument. And with that, Peter, I'm going to transition over to you next. You mentioned that you were a lead systems engineer. And my question is, as a lead systems engineer for the WHyMSIE mission, you've been at the forefront of integrating technology that goes beyond existing infrared and microwave tools. Can you talk about some of the challenges and breakthroughs of designing systems capable of penetrating clouds and smoke with such unprecedented detail, and how this technology could transform weather forecasting, wildfire detection, and even global safety applications?
Sure. Yeah. So I'll talk mostly about MBARS here. MBARS is a new type of oxygen or O2 absorption V-band radar. So Stephen was talking a lot about different wavelengths, right? We're focused around 60 gigahertz in this case. So MBARS uses differential absorption radar. That's several radar observations at very close frequencies to one another, and there's different attenuations at each of those channels. And what we can do is we take the data and scientists can retrieve surface air pressure and vertical pressure profiles from that data, especially over ocean. So Stephen is doing temperature and water vapor. We're focusing on vertical distribution of pressure. So that kind of information is particularly helpful in weather modeling and forecasting, because your viewers probably know that pressure gradients generate atmospheric motion and they dictate air, sea, heat exchange, and they're important basically at all scales of weather patterns from synoptic to mesoscale. So today's models rely mostly on ocean buoys or maybe ship tracks if a ship passes, over a certain area. But these buoys are generally too sparsely spaced for really accurate predictions, or as accurate as you could be if you had more observations. So MBARS allows us to kind of test this theory of ours that we can estimate atmospheric oxygen content, and from that we can back out surface pressure and vertical pressure gradients. So if we can demonstrate that this works from an airplane, from the NASA ER2 in WHyMSIE, eventually the idea is to apply that technology to a satellite payload. And if you could do that, then you get much higher spatial and temporal, global coverage of pressure than is currently available to us. And in theory, that would improve the weather models. So that's the theory behind that instrument. But I'm mostly a systems engineer. Sometimes I call myself a mechanical engineer. So my role in working with MBARS for WHyMSIE was mostly in mechanical engineering and design. So I used CAD, or computer-assisted design, and SolidWorks to design and build the radio frequency subsystem. That's where all the microwave bits of the radar live. So radar engineers kind of came up with this really complex design. They laid out the initial design and the components required to make their system work the way they wanted it to. That includes things like switches and attenuators, calibration loads, things like that. So I took all of these components and I kind of carefully stacked them and rotated them, positioned them in this kind of small hermetic pressure sealed box. It's about like 2 feet by 1 foot by 1 foot. So pretty small footprint to fit something like, 30 or 40 different components. And the biggest challenge, I think you asked what type of challenges did we face? So the biggest challenge, I think, for my part in this design was kind of figuring out how to lay out the waveguides and fit them all in this very small, relatively small box. So when dealing with microwaves, it's kind of interesting. Normally you connect electric components with copper wire, right? But for microwaves, that's not a very efficient way of doing things. You actually use these hollow rectangular pieces of metal called waveguides. They're just hollow tubes. And the microwave energy kind of travels along those more efficiently than it would in a traditional wire. V-band waveguides are about the size of a USB cord, but they're rectangular, they're not circular. So that kind of gives you an idea of the scale. So I designed over 30 of these waveguides with twists and loops and bends to get, to connect these components to all these, different positions in the box. And it's now this really complex web of twisted curving metal. You basically can't even stick your hand in this box anymore. It's so packed with objects. We affectionately call it the roller coaster. Everyone calls it the roller coaster at work because it just looks like this big loop-to-loop design. And what I thought was most impressive was that we actually got this right on the kind of the very first try, which I thought was, impressive considering how complex it was. So it required that I positioned everything correctly and also, connected the various components correctly. And then it also required that the waveguide machinists do their job correctly and bend things the right way and not make a mistake. So we got that right on the first go around, and MBARS flew over the summer for its test flights. We collected some pretty good data then, and I think we had 3 flights for WHyMSIE this fall because we were mixed. Half of our flights for WHyMSIE were with a different radar called CRS. That's a cloud radar at 90 gigahertz. So we flew MBARS for 3 flights at the end of WHyMSIE, and we got some good data there as well. So yeah, that's the basic idea behind MBARS, is to get this pressure data, apply it to weather models, and then eventually kind of put it in space and see where we go from there.
Wow, that's absolutely fascinating, Peter. And I appreciate you going into all that detail about MBARS. And I just wanted to say congratulations to you and your team for getting it done and getting it done on the first try. That is very impressive. So I definitely commend you and your team for your hard work in that regard. So this is just all very fascinating, and it's very exciting, to read about. So Peter, again, like I said, thanks for going into such great detail there. Jen, I wanted to transition next over to you and ask you this question. You mentioned your role as a scientific programmer / analyst. And my question is, as a scientific programmer / analyst for the WHyMSIE mission, you've contributed to processing and analyzing data from advanced tools that can penetrate clouds and smoke with incredible precision. Can you share how your role supports breakthroughs in areas like weather forecasting and wildfire detection? And also, too, what unique challenges you faced when working with data from such diverse flying conditions?
Yeah. So kind of going back a little bit to your first question, I guess just to reiterate, I had 2 roles with the WHyMSIE field mission. And so the first one was field support, and the second is that data processing afterwards. And so I guess a big part of my role is to make sure that I kind of help lay the foundation of taking data and making sure it's processed to the best of our ability so that other people who are scientists can confidently use CPL's data in their research. So I guess I don't do as much analyzing as setting everything up and then making sure everything is processed to the best of our ability. So like during our field mission, I'm making sure that CPL is working the best that it can so that it can actually, measure clouds and aerosols I think there was a couple of flights this year where we got some really great marine aerosols over the Pacific Ocean, some smoke plumes from some of the wildfires out west. And so I feel like that's like one of my biggest contributions to WHyMSIE is making sure that CPL is working really well. Now that WHyMSIE is kind of over, I'm on my computer, writing code to help process CPL. I guess one of the unique challenges that we're kind of facing right now is when we do data processing, CPL is a LiDAR and there's a LiDAR equation and there's different components to the LiDAR equation. And one of the, I guess you can call it a term, is overlap. And overlap to me is a very confusing term to understand. I guess a way that I could explain it is it's a difference in the way the LiDAR receives backscattered light from particles based off of distance. So CPL sends out micropulses of light, and as it hits particles beneath, some of that light is backscattered back to the instrument, and that's what's being received. And that signal is being measured. And then we take that signal and we look at depolarization and a bunch of different other variables. And so depending on the distance away from the LiDAR, I guess you could kind of understand that the further the particles are, the harder it is for it to get back into that small little bandwidth of the detector. So there's a way that we have to kind of correct for that. And it is a very difficult process sometimes, and it can really change based off of different flying conditions. So, when we're taking off, sometimes at Edwards Air Force Base, it's 70 degrees outside, and we take off, the ER2 reaches cruising altitude, and it could be like negative 20 degrees Celsius or negative 4 degrees Fahrenheit. And that is a drastic change. And so that can sometimes affect how our instrument collects our data. And then, when we go back in, we kind of have to finagle with some of the data. And so the overlap right now, I've been working on with Patrick Selmer, another SSAI employee. We've been kind of working through and making sure that it looks good. So you look at it based off of a theoretical molecular backscatter curve. And so sometimes during our flights, it looks really good. And since we have 3 different wavelengths, we have to kind of make sure that they all match really well. And sometimes we have different overlaps for different flights. And then also for the different wavelengths, we might have to kind of finagle with it even more. So I guess that's kind of one of the most unique challenges I'm currently facing with the WHyMSIE data, is kind of making sure that that looks correct so that other people can use the data.
Wow, that's very fascinating, Jen. And I, like I said, really appreciate the information that you gave specifically with overlap as well. And I really appreciate you going into the science aspect of that, because usually what I would think in terms of overlap, I would just think of, how like your 2 fingers would cross and like overlap together to form an X. Yeah. That's pretty much what I thought you were going to say. But since you explained the science behind overlap, it's very fascinating in terms of like the particle distance and the challenges that you have with bringing it back together as a whole. So that's incredibly fascinating. And just as a side note question, you mentioned you got some great photos from some of the missions as well. I would assume these pictures are like available on the WHyMSIE site or the NASA website. Is that correct for our viewers to check out?
Yeah, so for CPL, a lot of our data is on CPL's website.
Oh.
But yeah, you can always go there, and I'm sure that on the WHyMSIE website, there's probably a little link to go look at CPL's data.
Awesome. Very good. Well, for those of you audience and viewers who are currently listening, we certainly will be providing a link to have you all take a look at the CPL data. So please definitely click below in the video description of this video for you to be able to see that link as well. So it's going to be incredible data. And I just can't wait to see some of the data that has been collected and will continue to be collected. So with that, Stephen, Peter and Jen, I just wanted to thank you all so much for the time that you took out of your very busy schedules again to meet with me today in regards to your work that you have done at SSAI and in regards to the WHyMSIE mission. You all are truly rock stars who are really making an impact and a difference globally, and everybody around the world is going to continue to be fascinated by the great work that is going into this mission. And please stay tuned, everyone, for further updates. With this mission, we definitely will be reporting some more data. So please definitely continue to like, subscribe, comment, and follow SSAI. And please don't hesitate to reach out to us with any of your questions. I also wanted to make you all aware that on January 12th through January 16th, SSAI will be exhibiting at the American Meteorological Society, also known as the AMS conference down in New Orleans at the Ernest N. Morial Convention Center. So if you are in New Orleans, please definitely come and visit SSAI at exhibit hall booth number 434. So please come, explore great opportunities with us, learn what we do, and also apply for some cool opportunities. We have job openings in a variety of different fields, and if you are passionate about science, exploration, and humankind, SSAI is the place for you. So please definitely check us out, and please stay tuned for further updates in regards to what we're doing at AMS. We look forward to seeing you. Jen, Stephen, and Peter, like I said, thank you all so much for your time, and we look forward to the continued updates that come with the WHyMSIE mission.
Thank you.
Yeah, no problem. Thanks.